Okay, my goal for today is to get to the either effective or quantum action. I mean, both names are kind of misleading because, I don't know what's effective about it, but it's quantum only if you're doing quantum mechanics, but it's much more general than that. So to motivate it, last time we did this incredibly boring thing called, at least boring to me, Wick expansion. And that was based on observation that if you have a relation between partition function and its logarithm, so this is, everything. This is just connected parts. And your action is so-called free action, meaning no interactions, just a snail wandering around. So if your action is S of phi equals actually W of phi equals you start someplace, you end up someplace. This is the propagator we computed the first week, 1/2. That's the only thing that happens in the theory. And so to get all possible things, you just have to figure out the exponential of that thing, and then you separate your action into this guy. Plus the rest, so-called interacting part. And this part can be exponentiated that way, and that part I use the trick that ddj acting on z of j is a field inside some minus signs, who cares? So we did that last time. Now we'll take a more kind of physically intuitive approach, and we'll say, when I look at this integrand here, it starts with a quadratic part. So if interacting parts are very small, this is a Gaussian, and in the case of this equal to 0, it's exactly Gaussian. So I know what it looks like, and if it has some small deformation from these nonlinear things, so this is some kind of extra polynomial times to the action, what I expect from the action is to have at least one minimum. You know, it's kind of dominated by the quadratic terms in here. And it's something slightly deformed. I'll do this in more detail, but, you know, Laplace observed that if in this exponential I have something that looks like that, I will be dominated by the extremal or saddle point, or whatever you want to call, but basically extremal point. So I'll be dominated by derivative of that thing equals 0. And that means that derivative of the action there will be a value of this many-dimensional. I can only draw two-dimensional fields, but many-dimensional field I'll call classical for obvious reason in a second. When I take derivative of this term, I just get the sources. And this equation you know from classical mechanics. So, you know, this is derivative with respect to field. So if you own a lattice, this is some discrete index. This is the discrete index. This is the value of the source field on that lattice point. And this equation is called Euler-Lagrange and this is what you get from Lagrangian formulation of mechanics. This is the action associated with particular configuration. In mechanics tends to be in time, but for us it'll be in space-time. And there could be one solution to this. So if you do electromagnetism, the solution tends to be at the origin. Go ahead.
What does the C represent above the slide? Like the phi C?
C for classical. So and I'll actually, work out some lattice example, which I find helpful. So if you have a bunch of sources, this equation has a configuration, or maybe several configurations, but in this case, the way it's drawn, only one, which you actually solve by hook and crook. So, if your action, I don't know where it helps, but, if your action in continuum is integral over, some coordinates, I don't know. 1/2 a field that depends on a coordinate, Laplacian plus, let's say, 1/3 an integral over. Okay. And this guy is not, it's so-called inverse of the propagator. And if you do one functional variation with respect to the fields, so this is a, in continuum. I'm actually very lucky because, in teaching you this, I belong to the French school. I learned this from people in Paris a long time ago. And one of the other students, younger than me, but looks at least as decrepit, his name is Francois. First name, last name, whatever. Well, I've given you a link. He does it in my notation, or I do it in his notation. So if you follow the link to Francois, he'll do everything in continuum, and he'll write the correct x's and all that. So you'll be happy. But basically what happens is when you take a derivative, you get rid of one of these guys and you get an equation, just to give you some feeling, let's say in one dimension or spatial dimension, or let's make it two spatial dimensions. Of phi of x plus 1/2 phi squared of x. And the Euler-Lagrange says this should be 0, or it should be sources if you're doing something that's inhomogeneous, J of x. And that's kind of equations you have to solve for vibrating strings and membranes and whatever. So that's an example of a classical, or what I like to call deterministic Euler-Lagrange equation. So at this point, there was a miracle that this, in all cases we work with, this turns out to be classical action. And now you have a direct connection to classical physics, because if you solve it, these are just classical numbers, just ordinary numbers, like in a cavity I put charges on a boundary or something. And this might be the classical potential field or some field, whatever the field is. There is nothing quantum mechanical about this. You use your education to solve it. And I'll use some lattice example. I'll be able to solve a bunch of them by hand. And Laplace says this is the most important part of this whole potential, because it's smallest here, so it's least suppressed around the classical value. And an approximation to quantum mechanics or quantum field theory that starts here is called semi-classical approximation or WKB approximation or whatever. It says that the backbone of your quantum mechanical problem, where field can fluctuate, take values every place, and depending on values of the fields, this weight varies. And again, I'm being sloppy about I's and H bars, etc. You can put them in if you want to put them in. That's fine. But the main idea is that you can compute for any classical field, you can compute this quantity. So that says that I can now approximate, and again, I'll do it more carefully, but I can approximate the partition function by its classical value. I want to remove that, definitely. Times other stuff. So that's like the crudest approximation to path integral you can do. And if there is only one solution to this condition, there will be only one term. If there is some finite number of solutions, you have a landscape, and there are other places, ridges, tops of mountains, other bottoms of valleys. There will be some of classical solution, so that's allowed. And now what's amazing about quantum mechanics that already on this level, because I've been hiding it, but there is an I over H bar here in quantum mechanics. I'm adding number of complex phases, and I see quantum mechanics on a purely classical level because the backbone is the classical solutions, but the path integral is actually saying of all the paths that I have, there are several that are dominant, and each one of them looks like quantum mechanical kind of path, with I's and H bars. So that's a step number one. And now you can interpret this equation, classical Euler-Lagrange equation. Here we had a very trivial kind of interpretation. It just had, 2-point propagator, and then all the vertices could be connected by it. That gave us one version of perturbation expansion. This one is, better, in my opinion, because it picks out, the physics of the problem, the classical backbone, which is very important. Now, I can, make a little bit more out of this equation by observing that the first variation is we tend to split this into quadratic part, the propagation part, plus the nonlinear part. So the first variation is a propagator ending in a current, ending in a field, I suppose. So and that is a minus sign because the action started, this guy is the propagator, free propagator, which is morally a Laplacian plus what's called Klein-Gordon mass, and originally, our likelihood to go finite distance before we die in probabilistic interpretation. And then, if I had, let's say, phi cube theory, I would go to the vertex. And it has two legs. And that thing now continues. And if there was a 5-4 theory quartic vertex, I would have 1 over 3 factorial, 3 legs going this way. And this is supposed to be my source term, which I denote by this JI. And there is the same, you don't write indices explicitly, but that has index side, that has index side, that's a propagator, etc. And now I can solve the Euler-Lagrange equation by multiplying both sides by inverse propagator. So here I get minus and now you have a propagator multiplying itself, so Rj, Jk, they're just identity. So I need some notation that says, this is not a propagator, it's just taking care of this index here. I get rid of this propagator here again. So I have a free index and then 2 propagators going onward. And that just is the source term, J. I'm not sure about the signs here. So what I'm getting up here in Vj, that, I don't know, classical approximation is the first derivative of it. Is minus and this is now evaluated for some j. Usually it doesn't have to be 0. Let's see. And I multiply this by the inverse propagator on this side. And I'm defeated by my own notation, so just do it on the level of the action. This part is all the interacting parts. God. And this part is what I call classical field. Multiply by the inverse propagator. This is my source term. And this has a minus sign. Da. This I got on this side because I moved it over there. And I get an equation. And if you're happy with the end result, you're okay. Otherwise, I'll have to work harder. That says that if I call this thing, put some kind of C here for classical. It's a function of my background source field. That equals plus the interacting part. So I'm sorry for the mess, but it's just rewriting the Euler-Lagrange equation as a quadratic part, this one, plus the interacting part, that one. And how do you solve this? It might, it's actually very simple, but it might not make sense to you. So I will solve it on a lattice explicitly in some very simple examples next time, probably, or next week. This is a function of a linear term. So for phi field theory, you will be done. You will just solve a linear equation. That's actually the original when we computed probability distribution. For nonlinear theory, it's easiest to understand diagrammatically. So if you have a classical guy, it equals, I propagate, remember, cross hatch means connected. So I propagate and end up on the source, plus I go, let's say if it's a cubic theory, I propagate and hit 3 vertex, and I get each one of them going in a connected classical piece. And then I recursively use this equation by substituting. Here, every time I do this, I get a function of sources of the source field plus more of these terms and more powers of the coupling. So what this becomes is a sum of trees. So it starts with J, and then it goes, this guy becomes a cubic term. This guy maybe picks up the source. And then I have to scratch my head what a combinatorial term is. So I think it's 1/2 because of the symmetry here, but doesn't matter. But eventually, the only terms that ever contribute to this have structure of trees, and they're organized by more and more powers of coupling, because each vertex carries a power of g. So this is of order, let's say, g to the 6. And then they end up in this external field. Sorry. So you get terms which are of form g to the some power, M, let's say, means M vertices. A tree, meaning no loops, just branches. Some combinatoric things, and then you get some power of your source field, J to some power. It's a multinomial, so you know, Ji1, J2. And this has the same indices that sum up. And the statement is that when you think diagrammatically, go ahead.
First, so is this for phi 3 theory?
I'm just doing phi cube. For phi 4, I would have
For the vertex?
yeah, I would have a vertex with 4 things, yeah.
And I don't understand where the, like, why are we drawing these, like, blob circles? Like, where are those in the equation?
Yeah, so it says, if I call this field classical field, it's a function of my sources. So, and you know, that's how we produced the propagator originally. We had a source, for example, probability 1 at being at this site, and then we added up all the things, and that gave us propagator probability to end up someplace else. But now, that's this term. But now, in the equation, and again, you know, the thing to realize is this is defined over space-time, this index, or you know, lattice sites. But now, because of nonlinearity, we have a function of that field contributing. Because we are, you know, we are evaluating this derivative for the classical field. So it's a nonlinear thing. So there are various ways of solving it, but one way to solve it is if you say this coupling constant is small compared to, you know, the basic quadratic part, then you can organize it in powers of coupling. And at each level, you get a tree ending up in a power of sources. And you have to now integrate over and sum over everything, right? Whenever I have a double index, I mean, there are some discrete indices or continuous, in that case, they're integrals. And this is just a recursive way of expressing the first derivative of the field, which is what we call phi classical, because, you know, this minus the source equals 0. So the first part of this comes from the quadratic expansion, and the rest is in interaction terms. So this phi classical is now explicitly expressed as a function of the source field J up to coupling power G. So that's a perturbative way of thinking of what is. Now, you know, it looks totally weird if you're used to use Lagrangian formulation or Lagrange equation to solve celestial motion or something, right? It's a nonlinear function. You know, the solution, the classical solution is some nonlinear function of coordinates. You know, it's an ellipse or worse. But, you know, this is one way of expressing the solution, which is what it is, and it doesn't make sense to you. But, you know, that's it's solved by iteration.
So are we saying that this classical solution,
Yeah.
which is just one thing, there's only one classical solution?
Well, it depends on how many settled extremal points are. So in general, there is some number, and in case I'll show you, there'll be maybe exponentially many. But in the simplest case, in quantum electrodynamics, for example, there's only one bottom, which is where there is no energy in harmonic motion, or 1/2 in quantum mechanics per oscillator, and there is no energy in motion of electrons and positrons and stuff like that. So in that case, that simplest case, you're actually expanding around zero fields classically.
But in that case, that's within a specific region where you have only one minimum. Are we saying that this classical configuration, which is just the one thing?
It's a solution of Euler-Lagrange equation, and it's a nonlinear function of the sources. And one way of inverting, finding this function is by solving by iteration.
Yeah, I'm just saying, are we representing that solution as the sum of infinitely many terms?
Yeah.
Each of which represent multiple things that were right in this bubble?
It represents a solution that when I'm pulling out, using my operators to pull out my fishnet, I never find a loop in a fishnet. I just find a bunch of branches. And that's what a classical solution is. So diagrammatically, it has no loops, and it's important for us because now I'll show you how to compute one loop correction to this. So the first thing is the classical solution is just a multinomial in the source fields in this approximation where you're expanding it in a small parameter g. Go ahead.
The quantum only comes in when you add loops to the diagram?
Yeah, well, here I have a classical thing, and when I actually add loops, I'll dress up this classical thing, and that'll be called the effective action. So this is a backbone. First, we have to understand, what's the meaning of this part, the leading term. And it turns out it only cares about the solution, classical solution of your classical Euler-Lagrange variation of your action. And one way to express it, which is natural because we're doing perturbation series in powers of g, to say these correction terms are small, so I can order them as a power series in coupling and then compute them term by term. So sometimes you actually, that's perturbation theory in classical mechanics. Sometimes you say, well, this is almost an ellipse. So let me study, what happens if it's ellipse plus a small variation, etc. But that's how it works out in field theory. Yeah.
So this looks like almost the Dyson-Schwinger equation, except...
Yeah, well, Dyson-Schwinger equation will be the correct one that include quantum effects.
Right, but I wrote it down, and it looks
Yeah.
very, very similar. I don't understand why the loops are not allowed.
Yeah, we'll do it next, but the Dyson-Schwinger equation says here I have to put some extra thing, which I'll try to motivate and derive. W1 plus the derivative with respect to phi c. There'll be an operator in there. And the moment the operator shows up in this equation, I can start eating my own tail. I can start getting loops.
D by dj is the thing that makes it work.
What is it?
It's the d by dj
Yeah.
operator that
Yeah, or in this case, it'll be d by d phi. But yeah, in the case of connected partition function and connected Helmholtz free energy or something, it's d by dj's. But we'll find out that it's more convenient to go from sources to fields to write the equation, and that's what will be hopefully the end result of my not very successful labors today. So anyway, so this part just says, if you think in terms of perturbation theory, you know, I expand this thing, and it has to satisfy the classical part of Dyson-Schwinger equation, which is called Euler-Lagrange equation. So the Dyson-Schwinger is a, you know, if you wish, quantum, if you think this is quantum and not stochastic, you know. It's a quantum sibling of classical Euler-Lagrange. So now, let me go one step further. If anybody of you is on Twitter, I've gone viral for some reason because I say that theoretical physicists only know how to do Gaussians. But this will turn out to be true in this case. You know, not only can we determine this classical point, but we can actually pretend that its neighborhood is parabolic, or, you know, looking like ellipsoid. It can be approximated by quadratic terms, and that we can do. So we can go a little bit further than just classical thing to do the next calculation. And how do we get there? So again, if these trees don't make sense to you, better get used to them in the long run. But, you know, I'll solve something explicitly by hand. So, you know, you can see you can solve Euler-Lagrange equation in some cases. And if you decide to expand your solution in powers of coupling, that's what you get. There is, you know, no more mystery than that. It's one way of writing the solution in terms of finite number of couplings, and that gives you a finite number of sources, and you have to integrate over everything, and that's supposed to be the solution up to that accuracy. And so now, knowing that we can do not just quadratic part of this, we can decide to write the action as, plus this thing, plus phi dot j. We can expand this by saying, you know, if I have small quantum effect, everything is concentrated around the classical thing. So let me just say the original fluctuating quantum field, I'll write as classical one plus a small variation. So I write this as classical plus, I don't know, in latex this is called var phi. So this is just numbers, classical. I obtain it to give an accuracy by iterating my Euler-Lagrange equation. So this is just a number. This is something that I'll have to integrate over in my path integral. So this is a quantum. What is it?
Why are we at it?
Because we will change the origin of path integral in such a way that action here is always centered on a classical value. Right? So we change in here, instead of looking at phis and their variations, we define a shifted field. So every field has a classical value plus phi. Then this is just a constant. So in this integral, I'll be just integrating over variations, right? Yes, I'm allowed to translate the origin of my field in this path integral. Because, nothing tells me what's supposed to be the origin. So now I change the origin so that every place along this, for every lattice site, it's a small variation, so it's 0 away from the classical value. I'm just looking at this neighborhood, right? And now I'll only keep parabolic, square term as approximation. I'll make errors that have to do with weak nonlinear terms when I do the Gaussian integration. So I have that this, and this is not a 0, that's just what's up in the path integral. If I expand this, around the classical term, then I get value of the action for the classical solution, phi c, plus the first derivative of the field. A value is, I'm just doing multi-Taylor expansion, right? Times phi c plus phi. And now I'm so bold, I take the second derivative, matrix of second derivatives. I evaluate it at the classical point. What do you say?
Should there be no phi c in the second term? In the back, yeah.
It'll cancel. I'll use Euler-Lagrange equation, right?
Like in the Taylor expansion,
Yeah, and you're right. I mean, we'll get to the usual thing, which is the linear term goes away. Well, you know, this is 0 by Euler-Lagrange because it's extremum of this combination, right?
Yeah. I'm thinking it should be the instead of phi c there on the very right. No, above.
This one?
Yeah, the one to the right. Yeah, I'm thinking it should be the other phi.
Well, you know, it's going to be a derivative plus, well, I mean, you know, minus j times phi. Is that better? And this goes away by Euler-Lagrange equation. You know, I'm at a saddle point, so there's no linear variation. So this vanishes, and I start with a quadratic term.
So I'm not sure what the j is. Are you extending the
Well, you know,
j here?
j is taken outside of the action,
Oh,
so it shows up here.
but then should that also be on the left-hand side then? Is that equation?
Yes, it should be here. Plus minus j dot 5. You're right. I mean, it has to be. Let's see. I have minus phi c plus phi times j, right? On the left-hand side. So this term goes in here, goes away, and what I have left is that doesn't cancel, right? I get. Are we okay now?
Yeah. They should have the same sign though, right?
This is the variation.
Yeah, but I mean, on the left-hand side, are they both? I thought they were both pluses, like S. And
They're both pluses, yeah. You're right. And then here, I get this is like a a matrix, a linear operator that acts on this. I'm okay now? So the in multi-Taylor expansion, what survives, the linear term goes away because of that. I still depend on the field. So now the question is, should this guy be there? I hope it should. Yeah, because I'll integrate over quadratic part and get something that's in J's. But the main thing is that this quadratic thing I can integrate. And that was, the first problem set or something that says that what I have here classical times j. And now I have the integral of fluctuations around the classical trajectory, e to the I'll ignore this I over h bar, but we can reinstate it if you want it. A matrix, if it's a finite system or a differential operator, second order differential operator with Laplacian in it. If not, so in classical mechanics, this is very important. It's called Hessian. So what the first variation in classical mechanics gives you, it gives you unique classical solution. What the second variation does, it gives you stability of that solution. But and now this is the integral we know how to do. So because this is a symmetric matrix, it's multiplied by same on both sides, so anti-symmetric part would not contribute. It can be diagonalized. We assume it's not degenerate, no zero eigenvalues. If there is, yeah, then we have to work harder.
The eigenvalues to be positive.
And they should be positive and non-zero.
Why would we expect them positive?
I mean, in the particular case that we are working with, you can see this in Fourier space. So when you look at the operator, the Laplacian here minus plus mu square identity, this will get contributions for potential, but let me just do first this part. Then if I do a Fourier transform of this, this will give me eigenvalue, which is, k square minus. So because in Fourier space this is a square with -1, this becomes, sum or integral over the eigenvalue. Well, on every eigenstate, I get a positive number, right? I get acting on a kth eigenvalue. I get k square plus mu square. Now this is designed to be positive. If it goes pure imaginary, you have oscillatory solutions. But if this is a positive real number, then all the eigenvalues are positive. Now, what you really have is in Hessian, when you look at this second derivatives, ij of the action, you get that part. You get, minus square in Fourier space. I don't plus the second derivative of the potential evaluated on the classical thing. So you have to make sure that this is positive, non-zero eigenvalues. If it's turned upside down, then you have to think harder again. I mean, in quantum mechanics, they all contribute, the stable and unstable guys. So I think, this can be positive or negative. Now, if this has a small coefficient in front of it, then it's dominated by the Gaussian. So for small couplings, you're fine. You're guaranteed that everybody is positive because the Laplacian or the propagator overpowers the small nonlinear corrections. Now we will actually also look at the limit where the corrections are big rather than small, strong coupling limit. But in this perturbation argument, that's where you are. So now this we know how to integrate. And for small nonlinearity, we know how to do it for free field theory. We even know how to do it for massless theory, but that's what I'm giving up on notes by Costello because they're all in a massless limit, and I don't think you should worry about it right now. In a massive theory, small correction, this is all fine. And we get a determinant of second derivative as a function of phi classical. And then because it's Gaussian, there is a square root. So you know how to integrate this part. Now, it turns out this part does contain loops, so I will show that next. And that's also, one of the first problems that you have to do in any mathematical physics course. If this is positive, so you can decide to write it up in the exponents. You can say my solution is the leading term was action evaluated for the classical thing. And then I can say this is positive, so I can put here 1/2 logarithm of determinant of matrix, the Hessian matrix, second derivatives evaluate the classical point. So this is 1/2, and this is because you made sure that this is either positive or you take a positive part or you keep correct phase. The phases are called Maslow phases, etc. But you can do that. So modulo some imaginary phase here. You have an expression that I'm looking at determinant of the second thing. But now I use the famous identity that says that this is a trace of logarithm of S. So you're with me? Log of determinant is trace of a log of determinant is trace of the log for any finite determinant whatsoever that you've done some way or other. That's now, in continuum limit, these things are not matrices. You know, they become differential operators, right? This contains in it a Laplacian, discrete Laplacian. Continuum limit becomes differential. And then you have to start worrying whether this identity is true or to what extent it's true. And that's a bit of theory of linear operator I'll skate over. But basically, you prove that this thing is trace class. Meaning that even in a limit where your lattice spacing goes to 0, you're in continuum, the identity still works. Now, this is good news. If you were able to diagonalize this, so suppose this you write as some eigenvalue of this two symmetric matrix of some finite dimension. If you can diagonalize it, then the logarithm of that matrix, you know how to do logarithm on diagonal. It's just logarithm of each term. So if you define your eigenvalue, ith eigenvalue is e to the exponent I, then this becomes matrix of exponents. And the trace is the sum of the exponents. So, this just becomes sum of the exponents. So often, there are many ways of computing this, assuming that you know how to diagonalize this matrix. And sometimes you know how to do it, and sometimes it's hard. But right now, we are on a different path. We are on the perturbative path. And we say, well, I would like to express this thing as series in coupling constant. That's what we did with the classical part. We said we can compute classical part to any accuracy in small, fine coupling constant. Can I expand this object, the matrix of second derivatives? Well, when I look in detail what the matrix of second derivatives is, I get two derivatives of the quadratic parts. So I get minus 1 over, the propagator or whatever. Well, let's just call it a propagator. Plus, and now when I look at the extra part, I get second derivative of my potential, if S was 1 over plus second derivative of phi. If this is cubic, I just get here a coupling constant like this, and my field phi. Now what I can do is I can take this propagator out. Let's take minus propagator out. Put here the inverse. You know, this is a 2 by 2 matrix. And multiply the, well, when I take it out, I just get identity. Plus, you know, cubic thing. And this I have to replace by my derivatives when I put them up in exponent, etc. And now the trace of this quantity, trace of this Hessian in terms of phi's, will be something that, you know, starts with a cubic term, but then in the next order in G picks up a term like that, and then it'll pick out 1 over k. You know, I'm just expanding a log of 1 minus x is a sum of x 1 over k to the k. K equals 1 to 0. So what turns out is that this determinant can be expressed in terms of functions of the classical field, because, you know, this is function of the classical field, and the kth term will be order gk. So I have all corrections that contain one loop from this calculation. And this is a propagator, vertex, propagator, vertex. And if you count your h bars, you'll discover that correction is h bar correction. It's a first non-leading correction expansion h bars. And that's, you know, one loop expansion of the semi-classical field theory. It's accurate to the first non-linear term in the second derivative of phi. So there'll be other corrections. But this now organizes the calculation on the classical backbone plus one loop corrections every place. So that's, you know, one way of getting handle on the semi-classical expansion. We can do it. Now the rest is again not also pretty, because it'll be just Feynman diagrams of kind that we got also from weak expansion. But now the whole thing is sitting close to classical thing and fluctuations around it. So that makes sense to us. And Francois David does it very well. So watch that video, it's very good. And it's all in the same notation, it's not complicated. And, you know, I didn't get to the main thing. I wanted to tell you that this is now Legendre transform.